all my dear students. Before the start of this video session, let us first recite our mantra, that is stay at home and stay safe. Right? Let us start. Today we are going to discuss on steady state stability, which is the ability of synchronous machine to remain in synchronism after a very minute disturbance. We know disturbances are always present in a power system. Can anybody guess what kind of these disturbances are occurring always on the power system? Right. For example, there are gradual changes in load, manual or automatic changes of excitation, irregularities in prime mover, and so on. Obviously, these small disturbances cannot cause loss of synchronism unless system is operating at or very near to its steady state stability limit. This limit is the greatest power that can be transmitted on a specific circuit under specified operating conditions in the steady state without loss of synchronism. Right? You may kindly note that steady state stability limit is always greater than transient stability limit of the same circuit under same operating conditions. Let us see what the basic concepts related with the stability and what are the basic definitions. As said, power system stability can be generally defined as the ability of a power system to remain in the state of equilibrium under normal operating conditions and to achieve an acceptable state of equilibrium after being subjected to a disturbance. The disturbance may be small or may be large. May be small, that's why defined as the steady state stability, and if it is a large, that is due to fault, it is defined as the transient state stability. Right? After the disturbance, what is importance? That is after the disturbance, a stable system returns to a condition of acceptable voltages and power flows throughout the system. Figure 1 shows how power system stability may be divided into several aspects in order to make the problem easier to address. You can see this diagram. Power system stability, the three main classes are there: rotor angle stability, frequency stability, and voltage stability. Again, from our syllabus point of view, we are mainly focusing on the rotor angle stability. The rest you can see easily from this diagram. Right? Now, our main focus, that is on rotor angle stability, and its classification is given as in figure 2. Okay, so the main classes are steady state stability, transient stability, and dynamic stability. Again, from our syllabus point of view, we are having mainly focus on steady state stability and transient state stability. Right? Today we are going to discuss on steady state stability. Before the discussion, let us see what is the importance of steady state stability. That is why we are going to study this. Right? So, a knowledge of steady state stability limits is important for the following reasons. The first one, a system can be operated above its transient stability limit but not above its steady state limit. Second one, the transient stability limit can be raised by increasing the speed of clearing faults but cannot exceed the steady state stability limit of the final circuit. Right? These 2 points are very important. Then coming to the definition. A steady state stability. A power system is said to be steady state stable for a specific steady state operating condition if it returns to the same steady state operating condition following a disturbance. Such disturbances are generally small in nature. As these disturbances are small in nature, hence this is called as what? The steady state stability. Then what is steady state stability limit? The steady state stability limit is the maximum power. Note, it is the maximum power that can be transmitted in a network between sources and loads without loss of synchronism when the system is subject to small disturbances. Note that It is the maximum power transfer in a network between sources and loads. We are interested for the receiving power, not for the sending power, and in such a manner that the system is subjected to small disturbances, right? So this definition needs to be made more precise. In what manner? In the first place, where should be power measured? That is very important. From practical point of view, received power is important rather than the sent power. So this is to be understood even not stated explicitly in this definition, right? What is important? That is the received power. And we know that there is no advantage in sending power more into the line. Does not increase the received power but increases only losses. This is the first consider. What is the second? In second, what is the nature of disturbance? Because we are saying here that the system is subjected to small disturbances. So then what is the nature of these disturbances that ultimately causes the loss of synchronism if stability limit is exceeded? The disturbance is taken as a slow sustained increase in the load. It is what? Slow sustained increase in the load, right? And third one important, that is steady state stability limit is understood to be static limit, that is limit with the hand control, not with the automatic control with the devices. Okay, so this is what the precise definition of the steady state stability limit for understanding these concepts, that is steady state stability and what is the steady state stability limit. Okay, in the next session we are going to learn about the illustration of the steady state stability. Okay, thank you.